Good morning. My name is Seth Swaim and I am the Remote Sensing Group Director at Withers Ravenel. I have almost 20 years experience in GIS and GPS and the manipulation of remote sensing data. I've been able to extend that experience into the use of unmanned aircraft systems and remote sensing sensors to collect data for the purpose of mapping and surveying. We use this data every day in our Geomatics department to decrease data collection schedules and enhance survey deliverables. Today I'm going to be talking about a little more about how we do that in my presentation called Moving Data Collection to the Air. Within our Geomatics department, we have 5 groups. Our conventional survey group is actually made up of 2 groups, which is our construction staking and then our residential commercial design services. Then we have our subsurface utility engineering or SUE group. We have a full service GIS group that also does their own data collection. And then we have the remote sensing group, which is where I am. In our remote sensing group, we offer several different services. One being the drone and aerial operations, both LiDAR and photogrammetry from UAS platforms. Then we offer hydrographic bathymetric surveying and also terrestrial 3D laser scanning. So before we get started into the actual presentation, I always like to do a kind of a trivia question. So what is the difference between GPS and GNSS? And this is extremely important because all drones and surveying and mapping, there's lots of that technology that actually uses GPS and GNSS technology. So everybody's heard of GPS, but what is GNSS? So GPS stands for Global Positioning System. That is specifically the US-based constellation of satellites, whereas GNSS stands for Global Navigation Satellite System, which devices that have a GNSS chip in them can utilize GPS, which is the US-based, GLONASS, which is Russia, Galileo, European Union, and Beidou, which is China. So a GNSS system can utilize all of the different satellite constellations to come up with a geolocation of where you're at. So I'd like to get right into a project example to kind of pique some interest up front, show you a little bit about what we can do right off the bat, and then we'll get into some of the details on how it's actually done. So this is a reservoir survey completed utilizing photogrammetry, so flying a drone over the reservoir and taking pictures, and then using photogrammetry software to stitch those together. In the left-hand side, you can see kind of the lawnmower pattern is what we call it, lawnmower pattern of where the drone flew, and then all the blue dots are where the pictures were taken. The purpose of this reservoir survey was to do a volumetric analysis. The reservoir itself was about 21 acres, took about 15 flight lines to cover that area, 200 plus nadir and oblique photos, took both of those orientations. We processed that data through Pix4D and then generated a 3D mesh, 3D points and 3D mesh, which came out to be 6.5 million points that had XYZ tied to them in that data set. So we were able to use GNSS, UAS, and with a photogrammetry RGB sensor on it. Doing this for topographic 3D surface, and then also did an orthophoto. We set ground control and did an orthophoto. So this is a video of how that data ended up looking. This is the colorized point cloud. Then what we build what is called our gold surface for obvious reasons. You can see it's kind of a bowl shape there where they drained it and they had already done some earthwork. So these dots here represent what a standard surveyor would have gone out and done a 40-foot grid to do just a 1-foot or a 2-foot contour on this. So the surveyor still would have gotten additional break lines and additional additional data there wherever they saw on the ground where there would be additional break lines. However, they would not have gotten all of the additional inundations and in this data set, high resolution wise, you could even see some of the bulldozer tracks in this data set, which was pretty impressive. I'm going to switch gears real quick and take a step backwards a little bit, talk about regulations and what it actually takes to fly commercially. So we're flying under the FAA's Part 107 regulations and there's a few of those regulations here on the screen. Small SUS, UAS, which is less than 55 pounds. We do have to fly under visual line of sight, which is where the VLOS comes in. And then our max legal altitude is 400 feet above ground level. In addition to that, North Carolina DOT Aviation Division has put in place a permit, an operator's permit, to make sure they know that you know the North Carolina rules to fly. And then all UAS flown in North Carolina under Part 107 have to be registered with the FAA as well. Now we'll get into the hardware a little bit and talk specifically about some of the UAS sensors, whether it's RGB, a regular digital camera, thermal, LiDAR, which LiDAR stands for light detection and ranging. There's multispectral and look at vegetation. There's lots of different air quality type sensors or different sampling type sensors that have been mounted on drones, and then even sprayers using belly tanks and sprayers for herbicide and insecticides. Then there's lots of different types of aircraft as well. Most of what we use, or a lot of what the engineering world uses, is multi-rotor, whether it's quadcopter or hexacopter or octocopter. They do a really good job on small sites, and then can do, depending on battery levels and depending on what sensor you're flying, can do some very large areas as well, even up to 1,000-acre areas or very long corridors, depending on your workflows and depending on how you have your personnel set up as well, as far as visual observers. There are other types of aircraft, fixed wing, VTOL, vertical takeoff and landing. So there's additional types of aircraft that can have sensors attached to them as well. The multi-rotors are some of the most flexible as far as attaching either multiple sensors or different types of sensors on the same platform. One of the things that's important to understand from a UAS platform standpoint is the flight planning side, and doing that preliminary planning and whatnot to make sure that your mission, your UAS mission, that you're going out in the field to fly is successful. So you're looking at, there's multiple softwares set up to be able to help you do that flight planning. This is just one example of a software to where you can actually do autonomous flight. You can set up your area, set your altitude, set your line spacing or your overlap of how much overlap you need in your pictures, and set your speed, and then it kind of automatically lays out the flight pattern. And this is actually the flight planning for the reservoir that was flown in the previous project example. Here's another example of some flight planning software, and this video is actually replaying that. So some of the flight planning softwares allow you to track all the telemetry. If you notice the black screen on the right, it's tracking all the current telemetry of the aircraft. And this aircraft that's flying here is a DJI Matrice 600 Pro. So it's a hexacopter that's flying a LiDAR sensor, and this was a corridor survey flying along the right-of-way of a road to be able to do a utility design project to design do some water line replacements. And a lot of people will say, okay, well, there's a lot of planning that goes into play. Can you plan for everything? And sometimes yes, and sometimes no, as is in this picture. Uh, Best laid plans, and then you get out there and the cows decide to be using that part of the pasture that you need to take off and land at. Or they're not there when you take off, and then 20 minutes later when you come back and land and the cows decide to come over and check you out and see what's going on. I was assured that our guys were, while they were taking this picture, they were still watching the cows very closely, because that aircraft and that sensor are very expensive. One of the benefits to flying a large platform such as the Matrice 600 Pro, it can carry a large payload. And so in this picture, you've got a LiDAR sensor, Regal Minivux, one UAV LiDAR sensor, in addition to a Sony a6000 camera, which is one of the standard. It is a high-end LiDAR sensor, but it's one of the standard packages from a LiDAR and surveying mapping platform. But you're adding the high-resolution RGB camera as well in the nadir orientation, which allows you to capture photogrammetry or capture imagery at the same time that you're capturing the LiDAR information, which helps you on the back end in processing to colorize point clouds, create orthophotography, and you're able to do that because you're getting the high accuracy GPS locations, orientations on those pictures at the same time that you're collecting that LiDAR data. Now we'll talk a little bit about structure from motion processing, structure from motion software. You can see on the screen a handful of structure from motion softwares that kind of process that imagery into whether you're doing mosaics or orthophotos. Most of these software packages can use both nadir and oblique orientation pictures from the raw data standpoint. And the software package that you use a lot of times will revolve and be dictated by what you're wanting your deliverables to be. Some of these software packages are good from a mapping standpoint, and others are really good at doing orthophotography, but not necessarily mapping. Some are only good for doing mosaics and not necessarily tying stuff down to control. And so from a structure from motion standpoint, it's really important to understand exactly what your deliverables are so you can choose the software. A few more details about structure from motion photogrammetry from UAS platforms. Standard photogrammetry rules apply, as was mentioned, weather, all of that. But then in the imagery itself, typically the overlaps in traditional manned flight are 60 forward, 40 side. Kind of depends on your altitude and flight lines, but in UAS structure from motion, we typically do 80-80, so 80 forward and 80 side. Photogrammetry is the same on both sides. It's still limited to what the camera can see, and what it's doing is as you can see in the picture, you take those overlaps, you can build in the put in a stereoscope, look at the overlaps, and look at features in 3D. And so from that standpoint, the software then replicates that functionality based on those high overlaps, and can then build a 3D model based on that imagery. Here's a good example of a comparison of traditional or conventional manned aircraft imagery versus the UAS low altitude orthophotography. And so on the left hand side is your manned aircraft flights with that orthophotography, and that's the traditional 6-inch resolution pixels. And then on the right hand side you've got lower altitude, higher resolution. You can see a lot more detail, so you can see the pattern on that manhole lid, obviously a lot better than what you can see on that traditional manned flight. One of the other things that I like to point out on this picture is the skew in the building. If you look at the building on the left hand side, you can see the sides of the building a little bit, whereas on the right hand side you cannot. And so that's because of the line spacing on the flight line for manned flight versus the drone flight. the drone flight line spacing is a lot tighter, and therefore you can see you're always over those vertical structures, and so there won't be as much skew in those vertical structures. Now we'll go through some of our photogrammetry workflows and projects. Getting into the details of photogrammetry, it does require light. A lot of the same traditional manned aircraft requirements for photogrammetry apply. So it is very weather dependent, whether you're looking through clouds, whether it's sunny, whether you're a cloudy day, that sort of stuff is extremely important when you're doing data collection and feeding those images into a structure from motion software. Whether the ground is exposed, you're looking at bare ground. If you're trying to produce a 3D surface, bare ground is extremely important. Vegetation is very bad for obscuring the ground, and so you have to kind of do that in your flight planning and applying the right tool for the right job. Photogrammetry under UAS heading is a very low entry cost. From the drone platform and the structure for motion, it's not a big push to be able to do that. And photogrammetry does require a ground control if you're actually processing stuff from an orthophoto standpoint. Here's a project example for use case for photogrammetry, airport obstruction survey. So this is looking at the airport approach and departure surface of a specific runway to see if there's any vertical obstructions for that penetrate that surface. Since we are flying at an airport, in these cases, we're doing a lot of coordination with air traffic control and then also supplying NOTAMs, which is a notice to airmen that there is additional air traffic in the airspace of the airport, so that they can be aware, and we are always in direct communication with those airports, with either the controlling tower or airport staff, to be able to make sure that we have direct communication with them at all times. This video takes you through this project, this photogrammetry project of flying this airport, looking for vertical obstructions. So this gold surface here is the engineered surface for the approach. It is on a slant for the approach for that runway, and you can see the vertical obstructions of that are protruding through the surface, and then the red dots kind of at the terminal bud, so to speak, of those are the highest point of each one of those vertical obstructions to identify what's protruding. The next step would be to flag each one of those on the ground and then have a tree company go out and trim those trees or cut those trees down. And then we go back and refly those sites to verify that the vertical obstruction has been eliminated. Now we'll flip over and talk about LiDAR for a few minutes. Once you start talking about LiDAR sensors, there's a few details of those sensors that are fairly important. I'll hit a couple of these. Field of view is one of the more important ones, whether you're looking at the Minivux that does captures in 360 degrees, or you're looking at the Minivux DL that only captures a narrow band, such as if you're flying for corridors, or whether it's an easement corridor or a road corridor. Then scan speed matters from the standpoint of how many measurements per second you're actually getting, which gives you, it's a direct correlation to the density, your ground spacing for density of points to the ground, and then also is going to matter from the standpoint of how fast you can fly your drone to be able to capture that data. And then dropping down to vegetation penetration, which is extremely important from the standpoint of how many echoes can you measure per laser shot. For instance, the Minivux 1 UAV does 100,000 pulses per second, but it can measure up to 5 pulses returns per laser pulse. So that would be up to 500,000 laser pulses measurements per second. A few of the lessons that we've learned in collecting LiDAR data. The LiDAR sensors are capable of collecting a massive amount of data in a very short amount of time. However, they're not a silver bullet. They don't replace surveyors and boots on the ground. They cannot penetrate all vegetation. They're a specialized tool, and so understanding the capabilities and the limitations of those tools allows you to use the right tool for the right job. And then one of the large lessons is from a LiDAR standpoint, we are surveyors, and LiDAR is measuring topography on the ground and therefore does require a PLS in North Carolina. So we'll get into a few project examples here, and I'll try to go kind of get through these pretty quickly here. So sidewalk extension design survey. So some of the flight planning were the M600 platform with the LiDAR sensor, about 20-minute or 18-minute flight. We were able to collect about 20 million points on this project. And then we were able to collect 800 photos with that Sony a6000 camera as well, 24 megapixel camera. Here's the data set, the resulting data set in this road corridor project. As I said, this is for a sidewalk design project. We'll kind of go through the data a little bit here, and you can see the power lines, and you can see, and this is colorized based on intensity of return. And so you can see some of the vegetation has a different intensity of return than hard structures or soft structures. And so then we can colorize that point cloud, as you can see here. You can still see some of those power lines and some of those 3D features for that corridor, as well as some cars and different noise features that are in some of that data. And this is the raw data set. So this is starting to cut out some of that data to do some analysis. This is a culvert area kind of going under the road there. You can start looking at some of the data. So here's an inlet to where you can see that the LiDAR sensor actually penetrated through that grade inlet and shot the bottom of the box. You can see that by connecting some feature lines there, some flow lines, that those flow lines are basically kind of on the same plane there. Then pulling out features of the actual data set and doing some automation mapping based on some of that line work. Kind of gives you an example of that. This takes the data a little bit further. So this is the same kind of culvert area, but it shows you the finalized gold surface, or the finalized topographic surface of that data set, and kind of what that looks like, and what would have been passed over to the engineers for the actual sidewalk design, preliminary survey sidewalk design. Here's another example of a project that was combination of SUE, UAS photogrammetry, and LiDAR. So if you see on the right hand side here, you can see some of the SUE paint there. And so one of the functionalities of utilizing the high resolution, low altitude photogrammetry solution that we can do from drones gives us the ability to take those pictures, create an ortho photo with ground control, and then digitize that paint from the aerials, from the ortho photos, rather than having to survey all of those paint marks on the ground. Saves survey time in the field. Again, not a foolproof solution. If you look on the right hand or on the left hand side, you can see some tree canopy there. Obviously you cannot see all the paint that's under the trees, and so some of that still has to be conventionally surveyed and picked up, but there's an awful lot of survey of paint that can be mapped in the office via software solutions to save on field time and be able to reduce budgets and reduce schedules and get work done a lot quicker. And here's the LiDAR data set from that same project. You can see we kind of cut that data set in half. You can see the raw point cloud on the left hand side, and then that gold surface, and then the 3D lines, as well as some 2D CAD lines in that data set, and kind of shows how all of those data sets come together, and we can pass that data from our Geomatics department over to the engineers, whether those are internal or external, so that they can use it for design purposes. Here's another example of a good project that combined conventional survey, hydrographic bathymetric survey, and LiDAR survey as well. This video shows the LiDAR data set, and then the blue dots inside the little pond there are the bathymetric shots. And so we can strip out the additional vegetation and all the high vegetation, and this is just the ground, only the ground stripped out. And we can turn on the gold surface and show and then build a surface form from the bathymetric data that's collected via the hydrone and sonar, and then be able to show the mesh of being able to mesh those two surfaces together, and then show some of the additional conventional survey data that's collected with that on that project as well, and being able to merge all of those data sets together for a comprehensive project data set to deliver again to the engineers. So final takeaways: this technology is amazing, whether you're doing imagery for photogrammetry purposes or LiDAR. The data resulting from that can meet and lots of times exceed the measurement standards that surveyors are under for doing aerial surveys. And so the data is great, the technology is great, and offers up a lot of possibilities for data collection. I'll be available for any questions. Thank you very much.